We're going to solve all of these exponential equations. There are chapters in the description if you want to skip around the problems. The order we're going to go in is top to bottom on the first column, and then top to bottom on the second column. Here's our first problem. E to the negative x squared equals e to the negative 3x minus 4. Because the left and right sides have the same base, the only way they can be equal is if their exponents are the same. So we can set negative x squared equal to negative 3x minus 4. Then we can add x squared to both sides of the equation, and this is just a quadratic that we have to solve now. 0 equals x squared minus 3x minus 4. To solve this, we can factor the right side of the equation, and to factor this, we're going to need two numbers that multiply to negative 4 and add to negative 3. The choice that jumps out is negative 4 and plus 1. Negative 4 times 1 is negative 4, and if you add them together, you get negative 3. So that's the correct factorization. Applying the zero product property leads to the conclusion that x equals 4 or x equals negative 1. Again, if the bases are the same, then all we have to do is set the exponents equal to each other and solve. In this second example, the bases don't quite look the same, but we need to rewrite the right side so that it has a base of 2. Right now, the base is 4, but 4 is a power of 2, so here's what we can do. On the left, we have 2 to the 3x plus 2, and on the right, we would also like to have a base of 2 so that we can just set the exponents equal to each other. We have a base of 4, but that's the same as 2 to the power of 2. So 4 to the power of 2x minus 1 is 2 to the power of 2 to the power of 2x minus 1. But then by our exponent rules, 2 to the power of 2 to the power of 2x minus 1 is the same as 2 to the power of those exponents multiplied together. 2 times 2x is 4x, and 2 times negative 1 is minus 2. Again, all we have to do is apply exponent laws. We can just multiply those exponents together, which gets us here. Now the bases are the same, so we can set the exponents equal to each other. 3x plus 2 equals 4x minus 2. Subtracting 3x from both sides leaves a single x on the right side of the equation. Adding 2 to both sides leaves 4 on the left side of the equation, and that's our solution. This next problem is very similar to the one we just did. The bases right now are different, 9 and 27. However, they are both powers of 3. So we're going to use that fact to rewrite them with a base of 3. 9 is the same as 3 squared, so the left side is 3 squared to the power of x plus 1. And 27 is the same as 3 to the power of 3. So the right side is 3 to the power of 3 to the power of 3x plus 5. Again, we apply exponent rules. On the left, multiply those exponents together, and we get 2x plus 2. On the right, multiply those exponents together, and we get 9x plus 15. Now, the bases are the same, so we can just set the exponents equal to each other. 2x plus 2 equals 9x plus 15. Let's subtract 2x from both sides. That gives us 2 equals 7x plus 15. And then subtract 15 from both sides. That gives us negative 13 equals 7x. Then, dividing both sides by 7, we have that x is equal to negative 13 divided by 7. The next problem is again pretty similar. We can rewrite these two expressions with common bases. On the left, we have 64 to the power of 2x minus 4. But 64 is the same as 2 to the power of 6. So that's 2 to the power of 6 to the 2x minus 4. On the right, we have 128, which is the same as 2 to the power of 7. So we have 2 to the power of 7 to the power of negative x plus 6. Then we can just multiply the exponents together. So on the left, we have 2 to the 12x minus 24. And on the right, we have 2 to the negative 7x plus 42. Now that we've rewritten the expressions with common bases, it must be that the exponents are equal. So we set 12x minus 24 equal to negative 7x plus 42. We can add 7x to both sides to get 19x equals, let's just add the 24 to both sides. So on the right, we'll have 42 plus 24, which is 66. Finally, that gives us that x is equal to 66 divided by 19, and that's the solution. This next problem is very straightforward. We have 2 to the power of x equals 5. All we have to do is take a log on both sides. The base is 2, so we need to take the log base 2. On the left, we have log base 2 of 2 to the power of x. Of course, the log and the power are going to cancel out. And on the right, we have the log base 2 of 5. Now, log base 2 of 2 to the power of x, of course, is just x. And log base 2 of 5, we can calculate using the change of base formula on a calculator. So if we want to put this into a calculator, we'll just put log 5 divided by log 2. That's how, with a calculator that uses log base 10, we can calculate the log of 5 base 2. And this is approximately 2.322. Again, we have the variable in the exponent, so we just take the log using whatever the base is, and then use the change of base formula. We find the answer is about 2.322. This next problem is similar to the previous one. We want to get the exponential expression on the left all by itself. That way we can clean it up by taking a log. So let's subtract 4 from both sides. On the left, that's just going to leave 3e to the negative x plus 2. On the right, 5 minus 4 is 1. Then divide both sides by 3. So on the left, we have e to the negative x plus 2, and on the right, we have 1/3. Then we can take the natural log of both sides. Take the natural log because the base is e. The natural log on the left will cancel out with the exponential and just leave negative x plus 2. On the right, we have the natural log of 1/3. Now we just need to get x by itself, so let's add x to both sides and then subtract the natural log of 1/3 from both sides. That's going to leave an x equals the natural log of 1/3, but it's negative, and of course that's with a plus 2. Again, all we did was add the x to both sides and subtract the natural log of 1/3 from both sides. So we're left with x equals 2 minus the natural log of 1/3. If we plug this into a calculator, it is approximately 3.099. In this problem, we're again going to want to rewrite the equation so that both sides have the same base, and then we can set the exponents equal to each other. On the left, we have 5 to the x squared plus 4x. On the right, hopefully you can recognize that 1 over 125 is the same as 5 to the power of negative 3. Then, since the bases are the same, the only way these guys can be equal is if the exponents are the same. So x squared plus 4x must equal negative 3. We can then add 3 to both sides and solve this quadratic. X squared plus 4x plus 3 equals 0, and then we need to factor the left side. We need two numbers that multiply to 3 but add to 4. The obvious choice is 1 and 3. 1 times 3 is 3, 1 plus 3 is 4, and this gives us two solutions, x equals negative 1 or x equals negative 3. Here's another type of problem you might see, where again we've got to get common bases, but also we need to apply our exponent rules. You should note that the common base will have to be 3, because 9 is a power of 3, and 27 is a power of 3. So let's rewrite this. We have 3 to the x squared times 9 is the same as 3 squared. So 9 to the x is 3 squared to the x, and 27 is the same as 3 cubed. Then we can apply our exponent rules. 3 squared to the power of x is the same as 3 to the 2x because we just multiply those exponents. This is equal to 3 to the power of 3. Then we can apply more exponent rules. 3 to the x squared times 3 to the 2x is 3 to the x squared plus 2x. Just add the exponents together. And this is equal to 3 to the 3. Since the bases are the same, we can now set the exponents equal to each other. X squared plus 2x equals 3. Subtract 3 from both sides, and then we'll just need to factor. X squared plus 2x minus 3 equals 0. And to factor this, we need two numbers that multiply to negative 3, but add to positive 2. Thus, we're going to need plus 3 and minus 1. Those will multiply to negative 3, and they'll add to positive 2. Thus, our solutions are x equals negative 3 or x equals positive 1. Here's a problem where we have some action in the denominator. Actually doesn't make things very tricky at all. Let's just multiply both sides by that denominator to get rid of it. So on the left side, we have 500. On the right side, we have 20 times the denominator, which is 100 minus e to the x over 2. Again, we just multiplied both sides by 100 minus e to the x over 2, so that gets us here. Then we can divide both sides by 20. 20 goes into 100 5 times, so it goes into 500 25 times. So the left side is 25. And since we divided everything by 20, on the right, we just have 100 minus e to the x over 2. Now we want to get the exponential by itself so that we can just take a log of both sides to almost finish solving. To get it by itself, let's add e to the x over 2 to both sides, and then subtract 25 from both sides. That's going to leave us with e to the x over 2 equals 100 minus 25, which is 75. Then we can take the natural log of both sides. That's going to cancel out the exponential with that base of e, and that's going to leave us with x over 2 equals the natural log of 75. Multiply both sides by 2 to finish solving for x, and we have that x equals 2 times the natural log of 75. And this is approximately 8.635, and that's our solution. We've seen quadratic equations come up several times in these problems. This is a bit of a quirky problem because it's already a quadratic equation, but it's in disguise. We've got 5 to the 4x minus 10 times 5 to the 2x plus 25 equals 0. You've got to notice this does have the form of a quadratic equation because 5 to the 4x is the square of 5 to the 2x. So we could rewrite this in terms of a new variable if we wanted to. We could say u equals 5 to the 2x. That would mean then that u squared equals 5 to the 4x. And then we could rewrite this as a quadratic in terms of u. U squared, that's 5 to the 4x, minus 10u, since u is 5 to the 2x, plus 25 equals 0. And then we just have to use whatever methods are suitable to solve this quadratic equation. In this case, we can factor. It's u minus 5 multiplied by u minus 5 equals 0. That's because minus 5 times minus 5 gives us the plus 25, and they add to the minus 10. This, of course, means that u equals 5. But u is 5 to the 2x, right? That's what we defined u to be. So if u is 5, then 5 to the 2x must equal 5. But since those bases are the same, their exponents must be equal. The exponent on the right is just 1, so that means 2x must equal 1, and thus we have our solution, x equals 1/2. Pretty cool problem. Always make sure you're on the lookout for quadratics that are in terms of something you might not expect. In this final problem, we have to notice that we could take 4 to the 3x out of the first term and the second term, because the second term is 4 to the 3x plus 2. So if we take 4 to the 3x out of both of those terms, that leaves us with 1 minus 4 to the power of 2 by our exponent rules, and this is equal to negative 240. Now 4 to the power of 2 is 16, so this is the same as 4 to the power of 3x multiplied by 1 minus 16, and 1 minus 16 is negative 15, and of course this equals negative 240. We can then divide both sides by negative 15 to get that 4 to the 3x is equal to positive 16. That's negative 240 divided by negative 15. 16 then we can rewrite as a power 4. This is 4 to the 3x equals 4 to the power of 2, because 16 is 4 to the power of 2. But now, because the bases are the same, the only way these expressions can be equal is if the exponents are the same. So 3x must equal 2, and thus x equals 2 over 3. And there is a great big collection of exponential equations. I hope you found these examples helpful. Let me know in the comments if you have any questions, and check the description for links to other pre-calculus videos.
Persistent, couldn't even open myself up from air.